All right, so let's talk about Kirchhoff's laws. First one is Kirchhoff's voltage law, and this comes from conservation of energy. You might remember that voltage aka potential is energy per charge. That's its relationship to energy in the magic square. So what this means is, as a charge moves around a circuit as part of current, it needs to obey conservation of energy. And what that means is that if it completes a full lap of the circuit, it needs to end up with basically the same amount of energy that it started with. Going through a battery gives the current more energy. That's what the battery voltage indicates. And going through a resistor uses up that energy. So this rule says that essentially, as we go through a battery, however much energy we gain, we need to use up that same amount of energy going through the resistor. So another way to think about this is any path from the battery plus to minus must use up exactly that much voltage. That's one way to think about it. Kirchhoff's voltage law is sometimes also called the loop rule, meaning as you travel around a loop, any closed loop in a circuit, the voltage gains or increases must equal the decreases. Let's talk about what this rule means in terms of these three circuit diagrams. This first one is just a simple battery connected to a resistor. So the voltage law, or the loop rule, says that however much potential we gain, whatever the potential difference is between the negative and the positive side of that battery, I know this is the positive side because it has the longer line, that much potential needs to be lost as we go through the resistor. That energy gets used up, essentially. And what it turns into, we know that energy can't be destroyed. What that energy turns into is, if it's just a plain resistor, usually heat. So as we move through this resistor, the current goes through the resistor, the potential must decrease by V. That's what the loop rule is telling me. Now let's think about these two other circuits. These have special names, which we will learn about in a lot more depth pretty soon, but we're just going to focus on how the loop rule relates to both of these circuits for now. So I have one loop here, and I have two resistors. So now, as the current comes from the positive side of the battery, it's got a bunch of energy. Some of that energy will be used up going through this resistor, and the rest of it will be used up going through this resistor. If the current going through this resistor used up all of that voltage, it wouldn't have any push left to get through the second one. So what ends up happening is that this resistor uses up part of the energy, part of the voltage, and this resistor uses up part of the voltage. So this is going to lose V1 amount of voltage. Let's call this one R1 and R2. And as the current moves through this one, it will lose V2 amount of voltage. Part of the voltage through this one, part of the voltage through this one. And then these total decreases in voltage will add up to the total potential difference of the battery, which is basically like saying the amount of energy lost through the first resistor plus the amount of energy lost through the second resistor adds up to the total amount of energy lost. Okay. This is all in one loop, meaning that the total amount of decreases in the loop comes from these two, and then the thing increasing in the loop is just the battery. Now this last example is different. We still have two resistors connected to our battery, but in our this middle picture here, the current needed to go through both resistors to get back to the battery, meaning that part of the energy was used up through one and part was used up through the other. But in this circuit, an individual charge can basically choose. Does it want to go through this resistor, or does it want to go through this resistor? We could see these resistors as being parts of two different loops in the circuit. The result of this is that because it only needs to go through one of them, each of these, even though they might not be the same resistance, each of these is going to lose exactly the amount of voltage that the battery is providing. Whether a charge goes through R1 or through R2, it's going to use up all of the energy that it got from the battery just going through that one resistor, because it's going to go through one and not both. Okay. Now let's talk about Kirchhoff's current law. This comes from conservation of charge, meaning the charges can't just appear or disappear. They have to come from someplace. What this means is total amount of current in is always going to equal the total amount of current out anywhere in the circuit. This is true wherever we are. If we're just talking about this basic circuit and we were to look and see how much current is coming into this point in the circuit, the amount of current coming out is going to be the same amount. But this is especially important when we have things like branches here. So this is also called the junction rule. Because it describes when we have any branches or intersections in the circuit, what's going on with those. Okay. So in this simplest example, our current can't disappear, it can't go anywhere. We get the same amount of current around the entire circuit. Whatever goes into the resistor, however much current that is going to be equal to however much current comes out of the resistor. That means that if we were to connect a current meter, it wouldn't matter whether we put it before or after the resistor because it's the same amount of current going in as it is coming out. The resistor can use up energy, but it does not use up the charges themselves. They just keep going through the resistor. Whatever goes in comes out the other side. In this example as well, there's no other place for the current to go. So it's just going to be the same current all the way around. Whatever amount of current comes out of the positive terminal of the battery, that same current will go through this resistor, that same current will go through this resistor, and that same current will come back to the battery. There's no other place for it to go, so the current needs to be the same throughout the entire circuit. On this one, we do have some branches. And the current law, or the junction rule, tells us that the total amount of current coming in equals the total amount coming out. So if we think about this point in the circuit, this branching or intersection, we know we have some current coming into this point, and the charges want to get from the positive to negative side of the battery, so they want to get over here. And they have two options to do that. They can either go this way, or they can go this way. So some of the charges are going to go through R1, and some of the charges are going to go through R2, meaning that we're going to get some amount of current going this way, and then we're going to get some other amount of current going through this branch of the circuit. We have some current coming in. Some of it goes this way, some of it goes this way. And then when they join back up, they'll both be kind of rejoining, and they will again come back to the same amount of original current. Since our original amount of current is being sort of shared or split up between two parts, we know that those two parts must add up to the original current. At this junction, the amount coming in is just the total current I. The amount coming out is both of these together, I1 plus I2, and we know that that's supposed to be equal. And then at this point, the total amount coming in is I1 plus I2, and the total amount coming out is I, and we know that those are supposed to be equal. So that is how Kirchhoff's current law applies to this circuit. The rest of them, it still applies, it's just less complicated because there's no alternate paths for the charge to go.